why do I hear this audio ting, 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 ting every time a participant comes in? Can that be disabled? It's irritating.
Yes. Ravi?
I've disabled it.
Yeah, I think Satish is there now.
Yeah, good. Satish?
It's not needed, right?
Yeah. So, Sanjay, Arijit, and Sunil, shall we start?
Yeah, I think we can start. So we have quite a decent number of participants.
Yes, Sunil, Sanjay?
Yeah, I'm ready.
So, very hearty good morning to everybody, and a very hearty welcome from the Center for Atomic, Molecular, Optical Sciences and Technologies, which is a joint initiative of the IIT Tirupati and the ISER Tirupati. So the CAMOST started functioning slightly less than a year ago, and this is the first center of its kind. CAMOST is the first center of its kind dedicated to atomic, molecular, and optical sciences and technologies, jointly hosted by IIT Tirupati and ISER Tirupati. We started functioning since last August when it was inaugurated by Dr. Mitra. And now we have had several activities, several seminars, webinars through the pandemic, including one international video conference, select proceedings of which will be published by IOP's Physica Scripta very soon. And we are very proud to present the first short course by Professor Sanjay Majumdar of the Indian Institute of Technology at Kharagpur. You know, Sanjay has done some excellent work, and I talked to him a few months ago, made this request to him, and our original idea was to do some lectures on the angular momentum properties of light, and that is something that we will eventually do. But we thought that it will be a better idea to have some platform built for it, starting out from introduction to quantum optics. And that is what we are launching this morning. We will have 10 lectures and another set of a few tutorials as part of this short course. So thank you very much, Sanjay, for accepting our invitation and for lending your time for this. We have had tremendous response to this. I think the large number of students registered for it, and many of them will actually be able to join live on Zoom, and many others will listen to the lectures live on the YouTube telecast, which is also being done simultaneously. So may I request Dr. Arijit Sharma. Arijit and Dr. Sunil Kumar are the program coordinators for CAMOST, and I request Arijit to please introduce Sanjay. Arijit?
Yeah. Yes, good morning everyone, and thank you for giving me the opportunity to introduce Professor Sanjay Majumdar. So I think as Professor Deshmukh mentioned, we have been very fortunate to have Professor Majumdar giving us this introductory lectures on quantum optics to a large audience. So Sanjay Da, if I may affectionately call him, did his PhD at the Indian Institute of Astrophysics under Professor E.P. Das. And then subsequently, he did a few postdocs at HRI, the Technical University of Munich in Germany, and the Institute for Nanotechnology as well. Then around 2005, he joined the Department of Physics at the Indian Institute of Technology, Madras, and subsequently he moved to IIT Kharagpur in 2007. He has been an associate professor at IIT Kharagpur since 2013. And Sanjay Da's research interests span quantum optics, atomic and molecular physics, many-body phenomena, ultra-cold physics, ultra-cold atoms, to name a few. And I hope our association with Dr. Majumdar will continue, and we hope to listen to his lectures on orbital angular momentum probably in sometime later this year. So I think I will leave at this stage, and I will request Professor Deshmukh to continue the proceedings.
Yes, I believe we are ready to go, and I will not come in the way between the audience and Sanjay. So Sanjay, please take over, and thank you once again for accepting our invitation. Sanjay.
Thank you. First of all, am I audible?
Yes, yes, you are.
Is this clear?
Yes, absolutely.
Let me check that whether I can share the screen. Is the screen seen?
Yes, it is visible.
Yeah, you can go full screen.
Yes, you can go to make it full screen, please.
Okay. So let me start. So by saying good morning to everyone whoever have joined through the Zoom meeting and also through the YouTube. Okay, so good morning to all of you.
Sanjay, so I think now in the presentation, so it is coming as a PowerPoint slideshow, but there is also a presenter view. So maybe you can try to disable that presenter view. Is it okay? Or?
Yeah, so should I switch off my video?
No, like you can basically go off the presentation view, presenter view.
Presenter. Okay.
Yeah, just to press escape.
Let me see that. Okay, just wait. I have to minimize screen. Okay.
Yeah, the presenter view is also coming on the screen, so that we can. So you can end the show. Yeah.
Yes.
So
yes.
yeah, in the slideshow, in the slideshow tab, can you go to the slideshow tab?
In the bottom tab,
top,
yes.
On the top slideshow.
Either through requesting remote control of a screen. Approve. Okay, whom would like to control this company using accessible feature? Okay, I have to give the permission. You want to control this laptop?
No. You can. No. It is not required. You can go to the slideshow tab on the PowerPoint.
Yeah.
Yeah. Let's see what comes here. No, it's
no. Could you please end the show? No, I mean, not just to go to the slideshow.
Slideshow.
End the show.
Is it okay?
Yes.
Now
it
is okay. Now it is
perfect.
Yes,
Perfect.
So yeah, I am not that familiar with the Zoom. Thanks, sorry for that. So good morning to everyone who have joined. Okay, for this mini course. So let me say thank you for joining this course, and I would like to thank special the CAMOST to organize such a beautiful scope for presenting this course, though it is in a small scale. Okay, but hopefully we'll be having larger scale courses. Okay, using the same platform. So I would like to specially thanks Professor Deshmukh, okay, for his constant supports and endeavors, and because of that we are able to make this course. Okay, hopefully this course will be successful. Okay, I wish for the best. And also I would like to thank Dr. Sunil from ISA Tirupati and Dr. Arjit Sharma of IIT Tirupati for their continuous and generous support helps to manage this meeting. So this course is mainly meant for the undergraduate and postgraduate students. Also that PhD student at the junior level, I believe that they'll be benefited from this. Okay, so it will be at the elementary levels. So now if you so if you see that content of this courses, okay, so that 10 items in the verticals, and I'll try my best to cover them, though may not be able to exhaust the subject, but at least will be able to present and give you some flavor of them. But what I need that your constant support in the sense that there is I believe that many of you should be with a pen and paper. So some of the statement which will not be proof will not be given. So you may try then and then and check that statement whether it's correct or not. Okay. So those are elementary things will be there. So you better to check, and it will give you some moral boost also on the subject. Also, there is a tutorial sections as you see in this vertical. So which will be done, I think, in the Wednesday and Friday, I believe at 4 p.m. Okay. So many of the assignment during the presentation, I'll point out which will be there. Also, one set of assignment will be given to you or will circulated to you. So please try them. And if you have any point to raise on the assignment, or if you think something to be discussed from the presentation or from the assignments, please let us know at least 10 hours before. Okay, so that we can prepare for them and present them to you on the tutorial sections. Also, if you have any critical doubt or detailed discussion, if you want to make, either you can suggest, we'll try to make it possible. So let me start. Okay. So, so this is the outline of this today's presentations, today's class. Okay. So what I'll discuss, okay, there are two different disciplines, one quantum mechanics, one optics, so which are very well established over a century and so. Okay, optics is, has a large history, okay, length history. So why suddenly we require them to merge? Okay, so that is a very important point. Okay, and if they are merged, what would happen? Okay, so that's why that origin of the quantum optics has come up. Second thing, why do we need to study that quantum optics? From your point of view, from our researcher point of view, what is so important? Okay, I'll try to brief them, okay, to my extent is possible in this short class. Okay, then definitely I'll give some references, mostly from the books. So the books I followed for this course will be stated, and you'll see that many other things, pictures, statements are there. There are also some very good YouTube lectures available by eminent speakers and scientists. Okay, so you will be able to see, and I have also maybe sometime I have taken some ideas from them. Okay, so I'll refer them. Then what I'll discuss, I'll start from the scratch, like which is the basic of the all this discussion is the simple harmonic oscillator, and you can establish everything from this from the knowledge of the simple harmonic oscillator, and you'll see that we require to quantize this system, okay, the oscillator system, and the second quantization energy will be very important for us, okay, which I'll try to explain. And then I'll, after then having the knowledge of the second quantization of the simple harmonic oscillator, I'll try to explain that how light can also be quantized in the same framework. Okay, so that will be basically today's outline of the presentation or class. Okay, so let me start. So what is quantum optics? Okay. So the different definition available in the literature. I'll try to quote from the encyclopedia. So, and if you see that encyclopedia statement, okay. So what you see that the quantum optics is a study of an application of the quantum interactions, okay, between the light and matter. It is an active and expanding field, and I would like to add with that is a vibrating field. Okay, so with this modern or present day, all technologies are dependent on these. Okay, so this is the field has both scope in experiment and theory. Okay, there have been enough progress going on in the developing the this subject in terms of the detecting, in terms of the generating the sources, the light source which will be quantized, or one more difficult will be that if the light is quantized, how do I know that light is quantized and how we can detect them? So these have been going on since the first part of the 1980s, that 80s decade. Okay, since then there have been a constant progress going on. So let me tell first the one of the further of this topic. Okay, American theoreticians, Roy J. Glover, his research helped this field to clarify how light can behave both wave-like or particle-like. And also, he has explained that, okay, what is the fundamental difference between the light which is emitted from the hot object, just like you have a light bulb, okay? So there is a glow from the light bulb, okay? So it's actually coming as a thermal radiation, or what to that light, what will be the difference between that and with the light emitted from the laser sources. So what will be the difference? Okay. So one thing actually which will be very important to understand in the subsequent slides, okay, that the lights which are emitted from the hot sources are incoherent. What is the meaning of the incoherent? We'll try to see it. Okay. So now point is that you may ask that why do you need to study quantum optics? What was the history? What was the advantage? What was the disadvantage? Okay. So let me tell you that till the first part of this last century, people are very happy to explain the phenomena in nature, almost all the phenomena in nature, either by Lagrangian mechanics or the famous Newtonian mechanics. So you can explain most of the things using that. Then there came that the new topics, the quantum of mechanics. Okay, so and this framework of the quantum mechanics have been explained. Okay, successfully explained for many of the phenomena, and which was required also. So and whatever the phenomena which was available in nature, now people started trying to explain them in the framework of the quantum mechanics. People are happy. So even when you talk about interaction of the light with matter, people are happy to do that using the quantum mechanics framework of the matter, but there light was not necessary to be the quantized. They could explain all the phenomena using the classical light. At the first part of 1970, what happened? There are some ideas which were known but could not be explained using that semi-classical idea. That means that light will be classical and matter will be quantum mechanical. So they will be treated differently. So that was not suited. So that so what about the way we are defining the light using the classical electromagnetic wave? Okay, that was not sufficient after that, but till that it was very much sufficient. So what was the thing that they were very successful using that idea that understanding that light as a classical electromagnetic wave is that whenever we have that absorption of light by atom or molecule or macroscopic object, or if there is some, let me see whether I can, sorry, I can, so are you able to see my cursor? A pointer should I use?
We can see the cursor. We can see the cursor, Sanjay. Go ahead.
Or when you are talking about stimulated emission by external light, okay, which excites the systems and provide you additional emission, okay. So all those phenomena, okay, were able to explain using that idea of classical electromagnetic wave. Even the free propagation of the light, interference, diffractions, the process by which laser light comes out from the crystals, okay. So all this process which was we were able to discover or explain using the semi-classical, which is popularly known as semi-classical model, where actually electromagnetic field was treated as a classical wave. But then comes some bright mind to explain some of the phenomena, like why an isolated atom, which is in its excited state, can spontaneously emit. And is there any explanation for that? Or more like that, there is a recent, not that recent, it has been almost 20, 25 years. There is a new kind of light has obtained that is known as squeezed light. I'll try to explain why it is called squeezed, okay, in my subsequent slides, okay, later on. So these lights have a lot of advantage, okay, due to its precise positioning or preciseness in the momentum. Okay. So these lights actually generates as an infinite pairs of photons, which we'll be discussing. So if you don't go with that word, please just avoid. But this light, there's a there are famous applications, okay, available in the gravitational wave detections. As you know that there's the LIGO experiments and there's many other gravitational wave experiments where squeeze lights are used. And because of the availability of this squeeze light, okay, people could get that very weak field possible to be measured. Present day, all those quantum technology, quantum sensors, even that the modern high-res quantum computation, a quantum computer, okay, all depends on this, okay, the quantum quantized light. Okay. So or in future, what we'll see that more and more application of this. So I believe that this is a naive justification for to study this subject, which has immense prospect, scopes, and future. So this is a beautiful picture published in, I think, some of the popular journal, 2015, where both the nature of the wave and particle are snapped, okay, simultaneously or together, okay, on a metal surface. And in previous to that, either wave nature or particle nature people used to do. But this EPF film people, they could do it on the nanowire, okay. From the electron emission, they could get both the nature together. And those who are interested, maybe look at it. It is a very, very important and good work. Okay. So that will give, I think, enough motivation to quantize, to study the quantization of light. So let me tell you that, that these are the references which I'll follow. They are books written by all these famous scientists, experimentalists. Okay, so I think that Mark Fox books was available among them the first. Okay, according to the history. Okay, and it is very nicely written, having both the theory and experiment. Uh, Books by Gilbert Greenberg, Alan Specht, and Claude Fabre. That is excellent books. Explain that everything from the first principle. It is very worthy to read that book. JD and Knight. Was a wonderful book in the sense that it has both quantum mechanics and, in addition, people who are interested about the quantum computation, they'll get very good flavor of this. I believe that first three will be, actually I would like to recommend fully, even the fourth one. And first three will be used, okay, for the presentation here. You'll be able, there was exercise given from on all, I think first and third one. Okay. You can just look at it. So let me start. Okay, let me start from the beginning. So let's start that simple harmonic oscillator, as I said. So we know that the way classically using the classical mechanics, okay, how simple harmonic oscillator is treated. Okay, so what we do that we can express this system in terms of its Hamiltonian, which is actually its energies. Okay, and this Hamiltonian can be written in terms of the few arguments which are known as canonically conjugate variables. Okay, so this P and Q clearly they represents the position and momentum. Index I's can be, you can think about it in three different directions. Okay, like X, Y, Z. Okay, or if you have higher dimension systems, okay, you can just treat it. Okay, or if you have a multiple particle, you can treat it separately. Okay. So there are a lot of scopes available. Now these Hamiltonian, which represents the energy, as you know, can be written in terms of kinetic energy and potential energies, and which we will be able to express in terms of canonical conjugate variables, that momentum and position. Okay, but this, you know, all that for the harmonic oscillator. Okay, this is your potential, which you can just plot it easily, half m omega square q square. Q is the position variable here, and these systems are oscillating with the frequency omega. M is the mass. So having these systems, okay, what we can do that we can find out that how the position and momentum vary with respect to time. We can say that, or we can derive their dynamics. That is, you can do it from the Hamilton equations. So you will be able to get equation of motions, okay, which I can, if you haven't done, please do it. I can leave it as an assignment, okay, and you can work it out. Interesting part, the solution will be oscillating, okay. So it has an oscillation part, okay. You can write it in terms of cos omega t plus phi for extra phase is given, okay. So alpha and phi is the variables, okay, which you can derive from the boundary conditions of the system. And if you take the time derivative of that, what you will get momentum, okay. So now, in the case of quantum mechanics, the same system, if you would like to present, I have to just convert the canonical variables, canonically conjugate variables, position and momentum in terms of the corresponding operators. So operators we are denoting here with the hat. So wherever hat is there, you know that these are the operators, and these are actually used in the quantum mechanics. I think this all you know already. So once you know this, okay, that you have to write that your Hamiltonian, which now once we right? In terms of the operator, the Hamilton will be also an operator, and which you will be able to write that that Hamilton operator in terms of these canonically conjugate operators P and Q. Here, interestingly, that these two, that Q and P, as the canonically conjugate, they are non-commuting. That means commutation relations will give you here, as you know, is IH cross. Since these are mostly known by you, so I am not going in details all those things. I just trying to refresh your mind, okay, in these things, so that these are the things actually we'll try to make a recipe for the rest of the classes. So when we get the Hamiltonian operator in terms of this P and Q operator, okay, so we'll be able to get that from the Schrodinger equation, that non-time independent Schrodinger equation. We'll get the eigenvalue equation, where we can get that quantized energies as eigenvalues. Okay. And corresponding, the eigenstates, okay, will be giving as a basis for the simple harmonic oscillators. So what you see that here the index n is the quantizations. Okay. So why this is quantized, I'll try to explain in the next slides. Okay. So, but important point is that what you see that if you work in the quantum mechanics framework, okay, your energies will be quantized, and correspondingly you will get some wave functions, okay, which you can use as a basis or try to develop your solutions out of this basis. Now let's see that. Okay, before seeing the picture, let's look at the solutions. So the Q and P in the classical case, what we wrote in the real form as the real variables, okay. But what we can write it in generally, we can write it in a complex form with the complex amplitude A, okay, in both the cases, okay. And this is complex conjugate terms, okay. So now, in that, let me show the picture where actually you have considered that one bob, okay. So that this ball is actually having oscillations with a particular frequency, let's say omega. And as you see from the solutions, okay, that positions and momentums vary sinusoidally. And you can, if you like, you can draw a potential which is like a parabolic shape, okay, on this. But please don't go by literally, because I will, since I couldn't make this parabola more wider, I was not able to fit the full wave functions inside the parabola. But in classically, you know that that this particle is inside this potential, okay. And if you would like, okay, I would like you to work it out. If you haven't done that, you can have a phase plot in terms of the position and momentum, and which is like elliptical. So these are all the things you have done, I believe, okay, thoroughly in your earlier courses, okay. So if you have not done, please do it once again. It is worthy to look at. Now, if I make this potential instead of the wider to the microscopic, like if I narrow down, okay, what would happen? So once we narrow it down with a very micro size width, what would happen that this energy which I stored, okay, they'll be quantized. Okay. So in a narrow span of this oscillation, okay, what we will be able to see that energy quantized, and you will see that quantization and energy for n equal to 0, 1, 2, 3, like that. And corresponding wave functions, we will be able to see that I'll explain in the next slide. Maybe. That's better. So once we quantized, what we'll see that the quantized energy will be of the form of, okay, that h cross omega, which is the unit of the energies. And here what you get, that n plus half. N is the quantization number. Here I'll come details of this. Okay. here, if you use that Dirac formalisms, okay, what we can do, we can make this Hamiltonian in a dimensionless operator with a capital P and capital Q, where you see that this h cross by m omega square root of this is on the length scale. Okay, so if you just divide that Q by square root of h cross by m omega, okay, what we'll get is the dimensionless quantity. Similarly, we'll get dimensionless quantities P. The advantage is that now when we'll do this commutative relation in the quantum mechanics cases for this momentum and position operator, which are the canonical conjugate operator, you can write it in the dimensionless form as I. And that Hamiltonian you will be able to write in that format Q square plus Q square with the energy term free factors. Now Dirac, with his great mind of science and knowledge, okay, so he could suggest us a very beautiful way to tackle this. That is that he introduces, okay, that two different quantities or one single quantity and its conjugate, okay, that is a annihilation operator and creation operator. And here, the commutative relations is 1, okay. We can write this annihilation operator in terms of this dimensionless canonical conjugate operator, Q and P. So if we can write, let's say, okay, and one important point about the property of this creation and annihilation operator, as you see from this expression, they are non-Hermitian. That means you will not be able to measure them, okay? So it's not possible physically to observe them. Second thing is that this Hamiltonian operator, which you wrote in terms of Q and P operator, canonically conjugate operator, now using this definition of creation and annihilation operator in terms of Q and P operator, you are able to write in the form of this A dagger A plus half, okay, which is in the unit of h cross omega. And this is true for any kind of harmonic oscillator you will be able to write. So that means that you are able to write that Hamiltonian operator in terms of the creation and annihilation operator, which I will be able to see that how they work it in the next slide. But if you compare this form of the Hamiltonian operator with the energy, which actually you will get as a eigenvalue from this eigenvalue equation or Schrodinger equations, okay. So if you compare them, what you will be able to introduce that new operator, which is known as number operator, okay, as A dagger A, such that the eigenvalues of the number operator will be labeled as a quantization level, okay, which we have introduced in the last slide, or which we are showing it here in the case of quantization energies. So what you see it here, that if you operate number operator on these quantized labels, okay, in what we are defining it, we'll get that quantization level as an eigenvalue. So these states, what you see, okay, are the labels, energy levels, okay, and which will say that what is the level of quantization it is, whether it's n equal to 0, which is ground state, n equal to 1, perfect steady state, like that. So we'll see that they are the number state or number, and n is the number of corresponding number operator. So it is also known as Fock states, which I'll just explain it. So what we have learned so far. So like, if you want to treat that harmonic oscillator quantum mechanically, you have to write the Hamiltonian in the operator form of the canonical conjugate variables, okay, that is Q and P, and you will get Hamiltonian operator, which you are able to write in terms of the creation and annihilation operator, okay, that this annihilation operator is defined in this form. Yeah,
Okay.
there's any question?
Yeah, Sanjay, there is some question.
Yeah. So the first question that is related to the topic, that is why is this operator called creation and annihilation operator?
Very good. I'll come to that. Definitely. This is a very good question. Okay. So I didn't, so it was introduced and later on it is explained why it is. Okay. Any other questions?
Yeah, there are a few more questions.
Okay.
So the first one is, what is squeezed light?
Okay.
That is one question.
We'll come
And
to the, I think, third or fourth lecture, as you see in the topics in the vertical of the classes. Okay. So I just have it named. I just named them. We'll be able to explain that. We need to get a platform to discuss that. So I'm just trying to prepare the platform. So what you see is that.
Okay, Sanjay, one more question is there.
Okay.
yeah, so it's so the question is, the field of non-Hermitian physics has enabled new possibilities. So is it possible to measure the non-Hermitian operator by a weak measurement? Is the question.
Certainly, this is a question which is another level. Okay, so which we want to address separately because there's no scope to answer it. That weak measurement is another field. Okay, vast field, which will not be able to make others to understand using this framework. So at present, you take it that all the Hermitian quantities, because their eigenvalues are real, okay, we'll be able to measure them. So let's take it like. I believe that this is the answer for time being. Okay, so maybe we can talk about either in tutorial or later on. Okay, about the weak measurement and non-Hermitian. Certainly, there are non-Hermitian quantities like anapole moments and other things which are can be measured, but in a different ways. Okay.
So one more question is there. Why is the number operator A dagger A and not A dagger?
Right. So, that is a very interesting. So, what you see it will be if you just see it from the way. Okay, let me go back. Let me see whether I can go back. Okay. So, what you saw that Hamiltonian. Okay, here you can see that Hamilton is written in terms of Q square and P square. So, if you just write that Q and P, okay, in terms of A dagger and A or A and A dagger, okay. So you just substitute it and you will get it. It's not that we have put it by force, okay. Automatically you will get it from the definition of the creation annihilation operator in terms of the Q and P, okay. And when actually we saw them and compared them with the quantized form of the energy, okay, we just see that this has to be a number operator. I just forgot the first question. What was there? Okay, so creation. Why it is called creation annihilation operator, isn't it?
So there's one more. So in the lecture, it was told that until 1970, classical electromagnetic theory was sufficient to explain light phenomena.
Yes, that's true. So light was
but photoelectric effect. So, but photoelectric effect and Compton effect discovered in early 1900s cannot be explained using classical theory. So I think
no. The Compton experiment where actually light is treated as electromagnetic, classical electromagnetic theory. But the atom, okay, with which it is interacting, actually was treated as a quantum mechanics. Okay. So it is the interactions, okay, where actually matter, okay, was quantized, okay, and so you just maybe have a look at once again, okay. So it is interaction between electrons and photon, okay. So electrons are treated as quantum mechanically in the experiment, and light is treated as classical. I believe that's anything else. Okay, so let me go and maybe on the way actually we will be able to explain why the A and A dagger are called creation, annihilation and creation operator. So now see that from the Schrodinger equations of the simple harmonic oscillator, if we now write the Hamiltonian in the form of this quantized way, that is h cos omega a dagger a plus half, and we know that a dagger is some number operator. Okay, what we can write it that if you just see that number operator acting on the number state, okay, will give you the number state back, and what you will get that small n as the eigenvalues. So we'll get back the form of this in as the eigenvalue when you operate Hamiltonian on the number state. So number states which we are just obtained it is also a eigenstate of the Hamiltonian. Yeah, is there any other question? Okay. Now, so number state, as I said, I just earlier denoted by n, or you can write it as phi n, and they are designed as a energy levels. Okay. Okay. So
yeah, maybe this.
Yeah. Sunil, any questions? Maybe fine. So either you can write in terms of Hamiltonian, okay, and get the quantized energy as an eigenvalue, or you can write, okay, as in terms of number operator and get the energy levels. Okay. So in both cases, this phi n, which in short form we wrote n, okay, are actually number states, okay, which we'll discuss. Okay. Now next is that, which you can check it, the way we have introduced that A and A dagger in terms of P and Q operator. If you operate it on this number state, what you do that, it will that A dagger will bring the energy level from one level to lower level, just next adjacent lower level. Whereas A dagger will raise this energy level, okay, from that particular level, nth level to n plus 1. So this we can just work it out yourself. So then what would happen, that these are the not eigenvalue, these are the coefficient which one apply annihilation operator on phi n, and you can remember it by saying that, so for n minus 1, the coefficient will be square root of n, and for n plus 1, coefficient will be square root of n plus 1. Okay. So because this A dagger is able to shift the energy levels, okay, let me see that I can show that I can show this picture. Yeah. So since that this A dagger, okay, shift the energy levels, okay, from one particular state to the next energy levels, okay, and A is actually bring down, okay, to the particular level to the next lower level. So they are either called creation or annihilation operator, or you can say that they are the operator responsible for the energy raising or energy lowering. Important point is that here energy is quantized, not continuous. That actually you have to understand. Okay. So what would happen that when you just take these operators, okay, creation and annihilation operator defined by this way. So by this way, you can go, and if you, let's say that you go to the level n equal to 0. So what would happen to n equal to 0? So if you apply this annihilation operator, you will not be able to find any state below that. That means this application of the annihilation operator on this n equal to 0 level, okay, will bring you to a certain things where actually it's like a dead end. You don't have any scope to annihilate. Okay, that means you are in a position of equilibrium position. Okay, so there's nothing you can go, no way you can go bring down the energy levels. Okay, so that is that. So since it is a lowest in energy, you say that ground state. Okay, so that is the ground state of simple harmonic oscillator. So if you apply this one, ultimately what would happen? That is, since that is a dead end. nothing will come out, you will get the 0. So what we can designate instead of the phi 0, let us designate for the class, okay, it is whatever you like, but for the class, let us designate that phi 0 is a 0. So 0 state means that this is the ground state of harmonic oscillator. Okay, so it is writing wise, it is easy to write. Now let's see the properties of the ground states. Okay, so I believe you have understood why it is called raising and lowering operator, or in terms of energy, or its creation and annihilation. Its creation and annihilation is the sense that it is going to the higher energy or lower energy levels. Okay, so what you see that, one more thing, okay, suppose you want to go from ground state to the any particular state which is in higher level. Higher level means they are in excited level. Okay, so what you have to do, since you have only one transition or only one excitation is allowed to the next energy level using the A dagger, you have to repeatedly use this A dagger in times to go from ground state to the particular nth level. So what you do that, you have to sequentially apply this A dagger one after another and go to the from ground state to a particular state you would like to or you prefer to go. Okay. So as you see that, okay, let's see the properties of the ground state. Okay, as you said that if you just put the n equal to 0 in this expression, the quantized expression of the energies, what you will see that you will get half h cross omega. And from your intuition or from the understanding what you have from the classical mechanics, this is contradicting to that. Because in classical mechanics, what you say that ground state energy means that there's nothing is there, no potential, no kinetic energy. Okay, so ultimately energy will be 0. But here we have some significant energies. And what is that? Okay, so these significant energies are known as 0-point energies. Okay, that is popularly known. Okay, so that is at the ground level, what is the leftover energies? Okay, now can you try to explain that? Okay. So to explain that, let me go through some of the things which will be very important to understand. Okay, so here what you see that
there is one more question.
Right.
So the question reads: in theory, we use annihilation and creation operators to raise and bring down the energy. But experimentally, how is this possible?
Okay, so experimentally, okay, what you do, if suppose you have think about that, so that you are trapping one particle, okay, inside a small span of the potential, okay, so you bring down that yours, which I'll be terming later on the cavity, that is small enclosure, okay, of span, okay, where actually particle can move. Okay, so once you have the small span of this one, what would happen? You will get all these energy levels. Okay, now if you want to go from one energy level to another energy levels, okay, so what would happen? You have to gain the energies. Okay, so for that, what you have to do? You have to either shine a light, okay, from outside and let that particle, here generally call the particles because in the small span you have atoms or molecules, okay, from one state to going to another energy level state. Okay, so you need extra energies. So now all depends upon what would happen that where is your atom or molecules are situated. So if the atom is at the ground state, okay, so what you have to do? You just see that that by pumping the energy through a light, okay, and that has to be specific, you will be able to bring that atom to one energy level to another energy levels. Okay, or if you have that atom or molecule already in excited state, okay, already in an excited state, what would happen that it can, because of the tendency to go lower energy level, it can go to the any other lower level and emit light. Okay, so to go from ground state to higher excited state, you need external light. Okay, or if you want to allow the atom to go excited state to the any other lower state, it will emit the light. So by this process, experimentally, you can see. Also, what I'll talk to you later, okay, you can dictate the atom from which level to which level you can go. Okay, so that is one of the controlling mechanism which is advantageous in the quantum approach. Okay, so you will be able to control that atom to go in a particular state. So that is known as optical pumping, which we'll talk later. Okay. So
a few more questions regarding 0-point energy.
Right.
So the first is 0-point energy the characteristic result of quantum mechanics?
I'll explain it, definitely.
Okay.
I'll just explain.
And the second question is, does 0-point energy has anything to do with vacuum oscillations in quantum mechanics?
I'll explain. All those things I'll explain. So,
okay.
So that's the going thing I am just going to discuss. Okay. So I'm preparing for that. Okay. Now, yeah, this is a question which is very relevant. Okay. So thanks for asking, and which I know that this question will come. So what is this 0-point energy? Whether it's kinetic energy, potential energy, or is it a combination of this? Okay. So let's discuss and end this class today with that. Okay. So for that, what we have to just look at it, that we have to do some experiment. And in quantum mechanics, experiment means that you have to measure them, okay, repeatedly. Okay. That is that you take the expectation value of the measurement, okay, which is known as, okay, that you can write in terms of theory. So let's say that if I measure the position for the ground state, I use that position operator and, okay, X, which actually earlier I used to write capital Q, okay. So the both are same, okay, in terms of the ground state. So the ground state here, what you see, if you do the measurement repeatedly, and I'll talk about that, this is statistical nature we get. And here what would happen that you can take the expectation value, okay. I believe you know that what is expectation value, okay, from your mathematical knowledge. So what you can write, either X or Q, you can write in terms of creation annihilation operator. And if you take expectation value of the creation annihilation operator, what would happen that here A acting on ground state, as you know, it is 0. So A acting on the gate side of the ground state is 0. So while A dagger acting on the brass side of the ground state will be 0. So ultimately what you will get? The 0 values. So what you do that, once you do the measurement, okay, and if you take the mean value of the measurement, okay, what you will get, that you will see that the particle mean position, okay, will be at the center of the trap. If you are having the symmetric potential of the trap, or not trap, but I'm saying the harmonic oscillator here, okay, which I'll be defining as a trap later. Okay. So the mean position is, as you understood, is a symmetrical position at the center. Okay, you see that for all the states it will be like that. So what you see that it will be appeared like that, that your oscillator is grooved at the center. Is it true? Let's see whether it's true or not. See, if you just do it for the momentum measurement, that means you are taking expectation value of the momentum with respect to ground state. And I believe there's a mistake here, copy paste mistake. There's a minus sign is there, and I is there. Okay, so sorry.
So there's one more question that is relevant. So this is regarding the expectation value. So the question is the expectation value directly corresponding to the experimental data?
So, okay. So expectation value provides you that measurement value. Okay. So if you do the measurement, the whatever you do, okay, suppose you measure that position of the atom. Okay. So what you have to do here, you have to repeatedly do the measurement and get the statistical average. And that is what you will get when you do the calculate the expectation value. You are right that they from a single measurement will not get. Okay, you have to do repeated measurement, and then whatever the value will get, that will represent that the expectation value. Now, so sorry for the mistake. Please take it corrected. Okay, so when you do the momentum measurement, okay, also you'll get the zero value. Okay, so that means that ground state mean position and mean momentum, both of them are zero. Does it mean that sorry? Does it mean that the system is glued at the center? Does it mean that the system doesn't have any momentum?
Excuse me, Sanjay. I think there is some problem that people can annotate. Can you go to the top of your Zoom screen? So there will be an option for Zoom in the Zoom. So just click on that three dots on the right side.
If I go to top, yeah.
Yeah, there will be three dots on the right side. When you click, disable annotations for others.
So what I do?
Yeah, disable annotations for others. So when you click that three dots on the top.
Okay, disable annotation for others.
Yeah. So okay. Then, yeah.
Yeah, I saw some annotation.
Yeah, okay.
Yeah. Thank you.
Yeah. Okay.
So what you see that what we got it here, that we got the mean position and momentum at zero. Does it mean that that system is glued to the center, or does it mean that system doesn't have any momentum? So one thing what I would like to say that when you take the mean value, as someone pointed out, this is statistical average of repeated measurement. Okay, so that doesn't mean that the system is at that point. Okay, so system will be so what you will see that sometimes you will see that at the center as you got it. Sometimes it will be end from the center. Sometimes from the other side of the center. Okay, so when you take the statistical average of the different position, ultimately you will be able to see that the atom is at the center position. That is mean values. But what extent that will go, that when you do measurement, what extent that will be obtained, means we'll be able to find the particle in the span, or you will find the momentum, how much plus or minus momentum it can accommodate. So to do that, we have to find out the variance or standard deviation measurement. Okay, so that what you do that, as you saw that its mean is zero, standard deviation, sorry, variance will be just your the operator square, that is position square. So you can just write out that expression for the standard deviation or variance. Okay, so you will be able to write in terms of the square of the operator, and you just take the expectation value. And if you take that expectation value, this I'll give you an assignment that what you'll see that this value will be half. Similarly, P square with respect to ground state will be half. This meant that it is half in terms of the, I think, so I should tell that it is in the unit of H cross. So both of them are in the unit of H cross. What does it mean? It means that when you do this measurement of position and momentum, there is a spread of the observation from this central value or measured value, mean value. Okay. That spread is, okay, it can go from this side or that side of the measured value, mean value, okay, and that will tell that is half H cross omega and half H. So that is speed of this measurement, okay, which if you take the square root of that, you will get a standard deviation, okay. So that is we are denoting as delta x and delta p. So what you see that when you do the x square and p square, you see that the p square will tell you that what will be the kinetic energy. X square will give you that potential energies. So from the harmonic oscillator expression of the Hamiltonian, okay, what you'll be able to say that the position and kinetic energy it can accommodate, okay, at the ground state. So it does say that, okay, that you will have the particle is having the zero momentum and it is glued to the center. Okay. It has that it has a freedom that particle can gain some either kinetic energy or potential energy in terms of its. You can write as a very small quantity, as you see that it is a very small quantity in terms in the unit of h cos. So there is a fluctuation of the energies, so which is possible, okay, and because of that you will get that half h cos omega, the 0 point energies. This fluctuation of the energies, okay, either in terms of the momentum square or position square, okay, known as a vacuum fluctuation. Okay, what are you actually just trying to address it? That vacuum fluctuation, what you see that is nothing but the energy fluctuation at the ground state level. Okay, so because of this vacuum fluctuation, you can get the 0 point energies, and that you can fairly understood from this expression of the standard variance relation. Okay, so what you see, at least that whatever the spread is that, okay, we are telling in terms of variance or standard variance delta x. When you take delta x, okay, it will be square root of half h cross, okay, and delta p square root of or h square root of h cross by 2. So both will be same, okay, and ultimately if you multiply them, you will get the h cross by 2, and that is actually given from the Heisenberg uncertainty relation. Then it is the minimum limit that you can measure the position and momentum at the precision level. Hello? Sorry. So what you saw it here, that you got the ground state, and you see that how the momentum and position observation or measurement varies at that ground state level. And below that span, whatever the variation we got, it is impossible to go. So that is that minimum dispersion, what you can say, the minimum dispersion of the position and momentum, which we have to accommodate if you want to treat the system quantum mechanically. And that's why this state is also known as minimum dispersion state, or some people say that minimum uncertainty state. Okay, but advantage is that if you have that state at the ground level, and if you can keep that system at the ground level for a long time, you will be able to make sure that your dispersion is at the minimum level. So it will not spread as you are expecting. So that's the advantage of working with the ground state. I think let me stop it here because it's going beyond that time, okay, and try to address some questions and answers, okay. And from this onward, understanding the minimum uncertain state or minimum dispersion state, we'll try to develop the quantization of the light. Okay. Thank you.
So there are a few questions that I can see.
Right.
So the first one is, what is the cause of 0 point energy, and is the 0 point energy transformable, or does it follow any law of conservation of energy?
Okay, very good questions. Okay, so first of all, if you see that 0 point, what is 0 point energy? I believe that you have understood now. Okay, so it is the fluctuation of the energies. Okay, that's because that there will be spread in the measurement of the individual measurement of the position and momentum, which actually can be understood from the quantified from the expectation values, as you see it. Okay, so because of this, the spread, that means that electron is allowed, or particle or whatever system, okay, inside the potential or inside the harmonic oscillator is allowed to move and having that momentum. Because of that, you get the minimum uncertainty state. Okay, and and because of that, you get the 0 point energy. These 0 point energy is what you get. Okay, as you see that from the expression of this En. Okay, so sorry, is n plus half h cross omega. So these will be carried to all those state, excited state. So it is not a question of transfer. Okay, it is intrinsic to the system. So whatever system you take, it will be there. There is no question of transferring the energies. Okay, so it is something like that. Suppose if you have given a injection to someone, okay, so that there will be some pain. But how that this person, the person who is giving injection, how good he is, but there is some kind of minimum pain which you have to bear it. It is like that. So it is the minimum energy which will be always there in the system, okay, and which you have to carry it with the system. It is intrinsic to the system. I believe it answered to your questions.
Okay, so there are a few more questions regarding 0 point energy.
Right.
So first of all, does 0 point energy has any relation to absolute temperature, absolute zero temperature?
That's a very good question. Okay. So as you see that, if you increase the temperature, this is like a thermal. Okay. So what would happen that if you can have the extra term in the Hamiltonian. Okay. So that will be like a perturbation. What would happen that it will actually, depending upon the temperature, okay, what you can think about, it's like a thermal radiation may come, and that will excite the system from one level to another level. It will not do anything. It has nothing to do with the 0 point energies. Okay. So that, as I said, that even if you bring down the temperature at the level of 0, okay, this energy will be there. Okay. So this is something fundamental with the system, intrinsic to the system, irrespective of the position, temperature, ambience, anything.
Okay, so I also see a question that reads, what is single mode field?
Single mode.
Single mode field.
Oh, single mode. Yeah. So I'll come to the next class. Okay. So when we have this, we'll just quantize the systems. Okay. So what you'll see that in the quantization, okay, you will be able to write the system in terms of different modes. Okay. Like so those will be like a different basis element. Okay. So each of the element will be considered as a particular mode. I think I'll discuss in the next class. That is there. So please wait to the next class. Okay.
Okay. So next question about 0 point energy is 0 point energy characteristic of every central force? As a linear harmonic oscillator is an example of central force, so is the hydrogen atom.
Okay. So I think the way I have explained this one, okay. So this is explained in terms of the harmonic oscillator, and what you'll see, whatever you will do, whatever experiment or whatever natural phenomena you will see, everything can be represented in terms of harmonic oscillator. Okay. So this is one of the basic way to explain things. Okay. And once you write or once you expand the systems in terms of harmonic oscillator, okay, so what you will get, okay, you will get for that each harmonic oscillator, you will get that minimum energy, okay, that 0 point energy. So that will be there inside. So irrespective of the whatever system you choose, whatever potential you choose. So suppose you choose some kind of an arbitrary potential, not in central potential, but still you will be able to write that arbitrary potential in terms of this central field potential, okay, as a linear expansion or some expansion approach. So in each term we will get this kind of a harmonic oscillator, okay, and for each term you will get 0-point energies. So which you have to adjust when you do the expansion method.
Okay, there is a question that asks for some further explanation of vacuum fluctuations.
Sorry, what is the explanation of the vacuum fluctuation?
Yeah.
Yeah, I think what you got it from our discussions so far, that in vacuum fluctuation, as I said, I think it's a little bit clear that you will not be able to measure the individual measurement I'm talking about. Okay, you will not be able to measure the position and momentum exactly, okay, or together exactly. And here what happened that in this case, when you use the down state of the harmonic oscillator, okay, you will see that spread of this measurement, okay, when you do the measurement, will be of the order of h cross square root of h cross omega, okay. So then what would happen that you see that because of this limitation of the measurement, you are allowing the atom or whatever particle inside the harmonic oscillator to move or having some kind of kinetic energy or potential energy. Okay, so that will actually giving the freedom to the particle in the harmonic oscillator to have some kind of a energy freedom. So that is the minimum energy freedom which this particle enjoys, okay, and that is known as the 0-point energies. That's actually, basically, we can't go beyond that. Okay, there is a limitation from the uncertainty principle will tell us.
Okay, so the next question reads that can we say Heisenberg uncertainty principle actually causes 0-point energy? Does the 0-point energy exist for all bound state case in quantum mechanics?
I think I don't know whether you same thing I'm telling again and again. You see, the Heisenberg uncertainty tells that what is the limit, okay, and 0-point energy is the limit. But it doesn't mean that when you do measurement, you will always get the spread is of the order of square root of h cross omega. You'll get beyond that. And when you look at the squeeze state, what you will see that in particular this either momentum or position, particular canonical conjugate operator or variable, whatever you say, we will be able to squeeze this spread at the expense of the other. That means if you want to squeeze the spread of the position, okay, below that square root of h cross by 2, so then you have to say that you don't bother about the measurement of the energy of the system. So, like that electron microscope, where actually what we do that we are trying to measure the position of the particle. We don't bother about what momentum that particle has, what energy that particle has. Okay, so in that cases, okay, like in the LIGO experiment too, okay, where actually we want to see the how much the atom moves, okay, due to the gravitational wave. The small motion, the translation, okay, so that the amount of translation is important compared to that what is the energy of the atom, okay, or what energy it changes, okay. In those cases, okay, you can squeeze one of the quadrature. We'll name it in quadrature later on, okay, that the canonical conjugate operator, okay. One of the measurement span, you can squeeze it at the expense of the other. So here, what you see that these the Heisenberg uncertainty principle at least give you some kind of a limit, okay, below which you can't go. And ground state is one such limit where actually you are already in that, for both position and momentum uncertainty, you are already at the limit. Okay. So that's the advantage of the work, advantage with to work with the ground state, that you are having the precision. See the precision. So your position measurement precision and momentum measurement precision, you are at the best. Okay. You are not in a single point, but you are at the best. Okay. So that's the advantage of working with the ground state. Very good questions. Okay, I think this will help you that why this ground state is so important for quantum measurement, and which actually we want to exploit in the future. Yeah. Next question.
Sanjay, thank you very much. I think there are a number of questions, and we have gone past the time. Maybe we will take one more last question, and then
okay.
Yeah, last question, Abhik.
Yeah, so I see a number of questions over here.
Sure.
The last question that someone asked is 0-point energy and ground state energy same for all kinds of system?
Yeah. Thing is that, so this is as someone pointed out, single mode, or is a single particle. What we are talking about, single particle. If you have a n number of particle, okay, you have to just add them up. Like say what we saw it, okay. So you have a one particle. There's one particle for the ground state energy, or 0 energies. Okay, 0-point energy is half h². So on. There are 3 particles in the system. So if you are confining the system inside the harmonic oscillator, okay, 3 particles, you have to add them up. So depending upon that number of particles, okay, so this will be like linearly goes with that. So this will vary. Did I answer the question? I don't know.
Yeah, I think Sanjay, this has been an excellent morning. And you visited very fundamental elements in quantum theory. So I think this has been a great session. And I have also learned a few.
Is it too fast?
Sorry?
Speed is okay, presentation?
Yeah, I think so. I certainly think so. The pace is excellent, and let it continue. It can certainly be moderated as we go along the course, and we will see, we will get some feedback from today also. We will take that into account, and participants are, I would encourage them to send an email either to me or to Sanjay, and our email addresses are available. So send an email to either me or Sanjay and let us know. If you have any further questions, please post them in the chat box. We will try to take up these questions sooner or later, maybe in the next few classes. It's impossible to find time for all the questions in the same class, but I'm sure that as many as your questions can be answered as possible, and that certainly will be done. So Sanjay, very grateful to you for a brilliant lecture. I learned a few new things from it. I'm sure everybody did. So looking forward to the rest of the course, and we have a lot of persons to thank for enabling this short course. Sunil, would you like to do it on behalf of CAMOST?
Yes, sir. So first of all, Sanjay, thank you for accepting our proposal to put up this course. And so it is a very quick overview of the entire harmonic oscillator topic, and this is normally done in like several hours within a quantum mechanics course. So I hope that most of the students were able to really follow the basics. So I mean, those people who did not have much of a background, probably they can probably just look up those things, and during the tutorial section, they may be able to understand it much better, perhaps. Hopefully. Yeah.
So I'll send the assignment by today.
Yes. Okay. I think there were also questions whether they have to submit the assignment or
No, they don't have
they
to
don't need to submit it. But
can
these
raise
questions,
the point.
yeah, these questions will be basically.
We'll address them in the tutorial.
Yeah. Okay.
Right.
Okay. Great. Okay. Yeah. And of course, to enable these things, there were so many the support from all the, especially from the institutes, so the IIT and ISER. So the IT team who were in constant support with, for this enabling this, like even it is going to happen over the next few days, like in the same week, and then we have this tutorial sessions, and for all those things we needed need continuous support from this IT. So they are always with us, and I'm particularly thankful to the IT team, and of course the directors of the institute were very much supportive of enabling this. And I would like to thank the directors of both IIT and ISER, and all the colleagues who are the part of CAMOST. So they were all going to pitch in on different days to coordinate the sessions, and some of them are already here, and many of them will be also attending these courses. And also the students who are who volunteer to help us run this question and answer session, and all other technical help are also very much appreciated. So I think with that, I hope I have said thanks to all the people. If there is someone missing, please let me know so that we can.
So Sunil, may I ask something here?
Yeah, please, yeah.
Yeah, so I think some of the participants were asking if some notes or some material would be shared by.
Oh, yes, yeah. So I think Sanjay will be able to answer that question.
Yes.
I'll share the slides. Okay, the slides will be available.
Okay.
Yeah, one more thing is that there is a streaming YouTube link, and this will be available as in offline mode. Yeah, in offline mode, it will be available. So the students who missed the part of the lecture can always go and watch those lectures. Okay. So the link for that YouTube website has been shared in the email. So you can look at the bottom side of the email. So there the YouTube link is given. So you can always go to the YouTube, the official ISER Tirupati website page, where it is available. Okay. And the notes, how we will share and so on. So this will be made.
It is there in any textbook. So maybe they can look at it, and since YouTube link will be available, all the slides will be available there. So they can have it.
Yeah. Okay. So any other course material, we will let you know how it will be shared, maybe by email or something.
So Sunil, Sanjay, whatever material you want to share with the participants, please send it as a PDF to Sunil, and he will then arrange to have it sent to the participants.
Yeah, maybe we will make a Google Drive folder or something, which will be shared with all the participants so that they can have access to it.